The techniques that we developed so far for computing principal stresses and maximum shear stresses and the relative orientations of the coordinate axes have all been sort of analytical in nature. We have these formulas with the trig functions, and we also have this eigenvalue eigenvector method. What I'd like to introduce now is a graphical method, and this is something known as Mohr's Circle. It's named after Otto Mohr. And it's a graphical technique that allows you to see visually what all the possible combinations of normal and shear stresses that you can have on any coordinate plane in 2 dimensions. So this is a strictly 2-dimensional concept, though there is a slight 3-dimensional extension that we will talk about, but primarily it's really a 2-dimensional concept. And the way it starts out is by rewriting the transformation equations, the analytical ones, using the half-angle formulas, just in terms of the normal stresses in the x prime direction and the shear stresses on the x prime y prime axis, with this funny convention of having a minus sign here. So if I write the expression for the normal stress in the x prime direction and the shear stress, the minus shear stress in the x prime y prime coordinate faces, I can write them in the following fashion. I have this matrix that involves trigonometric functions of twice the angle of rotation between the 2 coordinate frames, sigma d, which we had defined earlier as sigma xx minus sigma yy over 2, and sigma m, the mean normal stress here. So sigma xx plus sigma yy over 2. So this is a way that I can rewrite. I've just really rewritten the relationships that we had before, but these relationships lend themselves to a geometric interpretation. In particular, it may not be particularly obvious looking at them, but they're actually the parametric equations of a circle that's centered at sigma m0. So let's go ahead and see how this works. So let me go ahead and set up 2 coordinate frames. I'm going to plot normal stresses, the sigma x prime on the horizontal axis, and shear stresses going down, sigma x prime y prime. So it's a little peculiar. I put the positive direction going down on the vertical axis there. But these equations are the equations of a circle. So let me go ahead and plot the center here. That's sigma m0. That'll be a point on the horizontal axis. And let me go ahead and plot the point sigma d minus sigma xy. That point actually, if you think about it, when I add it to sigma m0, is going to give me sigma xx, sigma xy. So that gives me a point. And I now am going to join the center of my circle to that point. This point is a point on the circle when theta is equal to 0. So I have no rotation. That represents the stresses or the traction components on a plane whose normal is in the x direction there. But if I put any non-zero value of theta, this point is going to move on a circle, and that's known as Mohr's circle. So I can actually draw this circle in, and if I move any angle to theta, I'll arrive at a new value of normal stresses and shear stresses that I can read off from the horizontal and vertical axes. So if I pick any given angle, let's say 10 degrees, I would move 20 degrees on the circle here, and I'd have a new point, and the coordinates of that point are actually the normal stress and the shear stress on that coordinate face. So the only tricky thing here is that you have to move twice the angle that you're actually physically interested in on the circle. And the intercepts of the circle with the horizontal axis actually turn out to be the principal stresses, sigma 1 and sigma 2, the max and the min. So it's easy to read off the circle. And the angle, or twice the principal angle, is just simply the angle from the ray going out to the point that you know to the horizontal axis. So once you've drawn the center of the circle and a point on the circle, it's easy to draw the circle, and then you can use the geometry of the circle to figure out all the angles and also the values, say sigma 1 and sigma 2 of the system. The maximum shear is the point at the bottom of the circle, tau max, and the shear angle is simply given to us as through the rotation from the point we know to the bottom of the circle there. And you just have to keep track of the fact that the rotations on the circle are twice the physical rotations, so we get 2 theta s there. So the steps of drawing Mohr circle are fairly straightforward. First you plot the center, that's at sigma m0. You plot the state of stress that you know on the x face, sigma xx, sigma xy, and you have to make sure that you put the shear axis, positive shear axis, pointing down. You then draw the circle using those 2 points, and then last thing is you read off the values that you're interested in from the graph. So you can just do this graphically if you only care about a rough approximation, or you can use some analytical geometry to precisely figure out what the intercepts and the angles on this figure actually are. Just a word of caution, when you do this, make sure you remember to put the shear down, and that angles are always twice the physical rotations. The orientation of the rotation, clockwise or counterclockwise, is the physical rotation, but the amount of rotation is scales by a factor of 2. So, but it's a very clever way of doing it. It also gives you in a single visual, all the possible combinations of normal and shear stress on any given coordinate plane. So if you start with xy, and now I decide to pick x prime, y prime, it's easy to see what the possibilities are. Or if I decide to rotate to another x prime, let's say x double prime, y double prime, it's also easy to see what's going to happen in the system just simply by looking at the circle. For instance, I know I couldn't have a normal stress with a negative value for this setup as I've drawn it here, or I could have shear stresses way out here or way down here. I know what the maximum and minimum values are. I know what the maximum normal stress is. I know what the minimum normal stress. So I have a bound on what can occur in the system here just by drawing this circle.